All right, welcome to the 11.3 video. This section is looking more closely at limits. So remember in section 1 we were talking about derivatives, and we had a definition of derivatives in terms of a limit, and this meant slope, right? The derivative, or the instantaneous rate of change, means slope. And then in section 2 we were talking about integrals, also defined in terms of a limit, but an integral is an area. Okay, and so in this section, we're looking at more calculations just of specific limits. Okay, so some definitions that we've looked at in the past, we have limits as they approach infinity. We have limits as they approach a number, and we can talk about that also from the left side or from the right side. Okay, so we're going to jump in with a few examples. Now, when we're calculating limits, as long as the function is continuous, so the question is, if the function is continuous, we can just substitute. So 2x minus 1 is continuous at 3. So is continuous at 3? Yes, because a line is continuous everywhere. And then we can just substitute. So now we have 2 times 3 minus 1, which is 5. So if the line or the function is continuous, then it makes our job a lot easier for finding the limit. Now, if we're looking at a limit as a value is approaching infinity, it works a little bit differently because we cannot say that a function is continuous at infinity because it's not a number. And so we can say, what is the behavior as a is approaching infinity? And one of the easiest ways to do that is by looking at what the graph's behavior is as our x-axis, or in this case our a value, is approaching infinity. So if we look at the graph here, a squared plus 3 is a parabola, and as a approaches infinity, f of x, or the function value, is getting higher and higher. And therefore we can say the limit as a approaches infinity is infinity. If it's asking for a value, then this could be described as not defined because it's not a value. The limit is not a number, right? Infinity is not a number, it's a concept. And so we can say that because this graph is continually increasing, the limit is infinity. However, if I'm asking for the value of the limit, right, L, if I'm asking for L, that's not defined because infinity is not a number. Okay. Now our last one here, what about the graph of 1 over n as n approaches infinity? Well, again, we can look at the graph here. 1 over n, remember, is that hyperbola. And so if we look at the hyperbola as n approaches infinity, so as our x-axis is going to infinity, our y-axis is getting closer and closer and closer to 0. Okay, so we can say that this is 0. The other way to think about this is as n gets really big, our denominator gets really big, 1 divided by a really big number is getting smaller and smaller and smaller and smaller. So this is like what we were talking about with the teacups as well. Okay, I'm not going to read through the brief history, but I encourage you to read through it. These are a lot of famous mathematicians that you might have heard of or you will hear of in calculus. So it'd be kind of nice to have an idea of where those people came from and what they did and how they contributed to calculus. Okay, so let's talk about informal limits. Okay, we have over 150 years in the history of defining limits, okay? And so there's a really complex way of defining limits, and then there's the kind of informal way that we have been using to define limits. And so we're going to continue using the way that we've been talking about since the beginning of the year, okay? So when we're looking at finding this limit, as we saw above, you can find limits algebraically, like we did in the first example, or geometrically, like we did in the second two examples, okay? To find the limit of this function algebraically, like we did back in chapter 2, we have to simplify the argument. We have to simplify this function so that it is defined when x is 1. So right now, see how we have x is undefined when it's 1, or the function is undefined rather when x is 1. And so in order to find the comparable function that is defined at that point, we have to factor the numerator. We have to see if we can eliminate this factor of x minus 1, just like we did with h in section 1. So to find the limit as x approaches 1 of x cubed minus 1 over x minus 1, we need to find the limit as x approaches 1 of, and we're factoring the numerator here. This is a cube, so it's a difference of perfect cubes. And so that's x minus 1 times x squared minus x plus x plus 1. Now there's a formula for that, right? If I have a difference of perfect cubes, a cubed minus b cubed, it's a minus b times a squared plus ab plus b squared. Okay, if it was a cubed plus b cubed, a plus b times a squared minus ab plus b squared. So you can think about it as, what would it be without the cubes? A plus b, and then I take a times a times b times b, but these two always have the opposite signs, and the last one is always positive. Divided by, denominator staying the same, x minus 1. Now we can eliminate that. And so we have the limit as x approaches 1 of x squared plus x plus 1. Now this is a parabola which is defined when x is 1. And so we can say this is 1 squared plus 1, which is 3. Okay, what about looking at this graphically? Well, if I graph this, I can plot it on my calculator. And so I go into y equals, and I type in parentheses, x cubed minus 1 divided by x minus 1, the original function. Graph that. And the question is, at 1, what value is it approaching? So an easier way to see that than the graph is to go into the table of values. And here's where we're going to see a trick, right? Because we know that it's undefined when x is 1, but we want to know what's happening really close around 1. So what we can do is go into table set. And what we're going to change is we're going to change the distance between these x values. So let's change delta, which is the distance between the x values, and we're going to change it to 0.01. And we're going to start the table at 1. So now when we go into the table, it's going to start at 1 and it's going to go up by these tiny, tiny increments. So we can see this is more than 3 and it's getting closer and closer and closer and closer to 3. And if we go up, we can see the values that are less than 1 starts below 3 and gets closer and closer and closer to 3. So we can look at these values and say, what are they approaching? Even though there's not a value when x is 1, they are approaching 3. Okay, so we look at the graph. Maybe I'll zoom standard. Oops. Zoom standard. So the graph looks like this. Okay, and when x is 1, we're looking at what's happening. And so we look at the table and we change the delta, the change in table, to 0.01, just so it's small increments. And then when we look at that table of values, when x is 1, 1.01, 1.02, 0.99, 0.98, we can see that the values are approaching. They're getting closer and closer, but they never achieve 3. That's okay. We're not worried about the f of x value at 3. We're worried about what's happening as x approaches 3, or when x approaches 1. And so we can say the limit as x gets closer to 1 of x cubed minus 1 over x minus 1 equals 3. Okay, two different methods of solving those limits. Let's take a look at the next page. So here we're actually calculating some limits, okay? One-sided and two-sided limits. Sorry, that was the wrong page. Here we go. Definitions of some of these properties. So with limits, we have the sum rule, meaning if I add two functions together, I can separate them. So if I had the limit as x approaches c of x squared plus x, I could take each limit separately, the limit of x squared and the limit of x. Okay, the same thing applies for the difference, and the same thing applies for a constant that's been multiplied, which is really just repeated addition, right? Notice the k just pops out front. So those three rules are very closely related. The next set of rules has to do with multiplication. So I can also do the same thing for when I multiply two functions. I can take the limit of each function, which means that I can do the same thing for division, taking the limit of each function, as long as the denominator does not equal 0. And then lastly, if I can do it for multiplication, I can do it for repeated multiplication, and therefore we have the power rule. And then this is unique because this doesn't usually happen for limits or for functions, but it does work for limits, that we can do a square root rule or a radical rule, which is that if I take the nth root of the function, I can take the nth root of the limit. So let's see how to apply these. In example 2, we're given the limit as x approaches 0 of sine of x over x is 1. That's information that we're given. And we need to use that in order to calculate these other limits. Okay, so I'm looking at this and I say, okay, well, the information I'm given is a fraction, so I don't necessarily want to use the quotient rule because I can't apply the quotient rule to get this fraction. Our goal is to get this same fraction so that we can just replace it with 1. And so how can I do this? Well, I can split this function over addition, right? I can use the sum rule. And so this is the limit as x approaches 0 of x over x plus sine of x over x. X over x plus the limit as x approaches 0 of sine of x over x. Well, x over x is just 1, and the limit as x approaches 0 of 1 is just 1. And so we have 1 plus the limit as x approaches 0 of sine of x, that's what we were given. And so this is also 1 from the given. And so our answer is 2. And we used the sum rule. In part B, I have cosine, I have sine. How do I substitute sine and cosine? Well, I know that sine squared plus cosine squared, sine squared plus cosine squared is 1. And so if I subtract cosine squared, then sine squared x equals 1 minus cosine squared x. And so I can actually write this as the limit as x approaches 0 of sine squared of x divided by x squared. Well, now both of these are squared, so I can use the power rule. So this is the limit as x approaches 0 of sine of x over x squared, which means that it's the limit as x approaches 0 of sine of x over x squared. Well, this was our given. And so this is 1 squared, which is just 1. And then our last one, I see they're both cube roots. It's important that their index is the same, both cube roots, and so we can use the root rule. And so this is the limit as x approaches 0 of sine of x over x. I'm going to write it as to the 1/3, but that's the same as the cube root. I'll just write it as a cube root, which is the limit as x approaches 0 of sine of x over x, all in a cube root. Well, the limit as x approaches 0 of this is 1, so we have the cube root of 1, which is 1. Okay, so that's a few examples of how you can use those rules. Okay, let's take a look at example 3. Now, if our function is continuous, as we were talking about in the warm-up, or in the beginning of the notes, in the vocabulary section, if the function is continuous, then we can substitute a. And if we can substitute a, that means the function is continuous. So IFF means if and only if. If and only if. It's a very common mathematical abbreviation. Okay, so what I want to know is, are these functions continuous at these values? Okay, and one of the ways that we can do that is we can use our graphing calculator. Or algebraically, which is the way I'm going to show you, we can use these set of properties. So the first question is, how do I split this up into functions that I already know? Well, notice e to the x I know, tangent of x I know, cosine of x I know. So we can use the quotient rule here. Now, we didn't use it above because we were given a value with a quotient already. Here, we're not given any values, so we want to use all of the rules to simplify this until we can calculate it. So the quotient rule is the limit as x approaches 0 of e to the x minus tangent of x divided by the limit as x approaches 0 of cosine squared x. Now I can simplify the numerator with the difference rule, which is the limit as x approaches 0 of e to the x minus the limit as x approaches 0 of tangent of x divided by, and the product rule with the denominator, the limit as x approaches 0 of cosine of x squared. Now, each of these functions I know the properties of. E to the x is continuous at 0, tangent of x is continuous at 0, cosine of x is continuous at 0. Therefore, I can substitute 0 here. So e to the 0 is 1 minus tangent of 0 is 0 divided by cosine of 0 is 1 squared. 1 minus 0 is 1 over 1 is 1. Sorry about the spacing. I plan to do all of that in one step, but I think it's clearer if I do it in two. Okay, so then let's look at part B. So for part B, we're going to do the same thing. I know information about the square root function, and I know information about the log function, so therefore I'm going to split this up. So we have the limit as n approaches 16 of the square root of n divided by the limit as n approaches 16 of log base 2 of n. Square root function is continuous at 16. It would be discontinuous at anything negative or 0. The log function is continuous at 16 as well. Same, would be discontinuous at negative numbers. So then I can substitute. So we have the square root of 16 divided by log base 2 of 16. Square root of 16 is 4. Log base 2 of 16, that's 2 to what power is 16? 2 to the 4th power is 16, so this is also 1. The answer is not always 1, but when I'm setting these up, I like to give you some nice numbers, and most of the ones on Math Excel turn out to be integers or common fractions like a half, or fractions that are easily simplifiable. Okay, let's look at this last page. All right, now back to example 4, which I had shown you by accident earlier. Okay, so example 4, we're finding the limits, but notice this is the limit from the left and the limit from the right, and then the limit from both sides, right? And we talked about this before. If the left and right limits don't match, then the two-sided limit, or the limit without a side, does not exist. Okay, so what we want to do is we want to look at what is happening here. Is it continuous or discontinuous at 2? So we need to graph this, okay? So if we take our graphing calculator and we put in these functions, negative x squared plus 4x minus 1, and then in the second one, 2x minus 3, okay, and then we graph it. Okay, so the question is, at 2, are these continuous? Well, it doesn't look like it, right? So each of the two graphs is continuous at that point, but it doesn't look like we'll have a two-sided limit. So let's find it. Well, from the left, right, if I graph this, when x is less than or equal to 2, we're looking at the parabola. So when x is less than or equal to 2, we have something like this. When x is greater than or equal to 2, we're looking at the line, which is something like this. Okay, that one's filled in, that one's hollow. So from the left, we're looking at the parabola. Limit as x approaches 2 from the left is when x is less than 2. Negative x squared plus 4x minus 1. Now a parabola is continuous at 2 from the left, and so we can substitute. Negative 2 squared plus 4 times 2 minus 1. Negative 4 plus 8 minus 1. That's 4 minus 1 is 3. Now from the right, from the positive side, we're looking where x is greater than 2. So this is the limit as x approaches 2 from 2x minus 3. Lines are continuous, whoops, from the right. Lines are continuous, and so we know that we can substitute 2 times 2 minus 3, 4 minus 3 equals 1. So just as we saw on the graph, these do not end at the same function value, and so this does not exist because the limit as x approached 2 from the left, I keep writing negative 1, it's just from the left, f of x does not equal the limit as x approaches 2 from the positive side, from the right, of f of x. If the two limits do not exist, then the two limits do not match, the two-sided limit does not exist. Okay, let's look at number 5. So we want to find the limit as x approaches 3 of this function here. And anywhere that x is not 3, we have that it equals this function. And just where x equals 3, we have this function. We want to know if it's continuous or discontinuous. So the way that we can find this is we can look at this function and we can say, what values is this function approaching when x approaches 3? And is it the same as this function here? So does the limit of x squared minus 9 over x minus 3 equal 2? That's really the question that's being asked here. Okay, now you can look at your calculator, but remember, we cannot always trust our calculators. So we want to find the limit as x approaches 3 of x squared minus 9 over x minus 3. Now remember, if it has an undefined value at where we're looking, then we have to simplify the function. So we can factor this. Difference of squares, x plus 3, x minus 3 over x minus 3. So this is the limit as x approaches 3 of x plus 3. Now x plus 3 is continuous, and so we can say this is 3 plus 3, which is 6. And the question is it equal to 2? No. And that means the function is discontinuous. Because our top function approaches 6 and then drops down to 2, and then it continues off from 6. So what this would look like is a function with a hole. So it's something like a hole that's filled in at 2, discontinuous. Okay? And then let's look here at example 6. For example 6, we want to find each of the limits for the integer function. Now remember the integer function, 0 until we hit 1, and then it jumps up, also called the step function. So we want to know the limit as x approaches 3 from the left. So we're looking when x is 3, and we want to look to the left. So the limit as x is approaching 3 from the left is going to be this value, 0, 1, 2, 3. So anything really close but less than 3 has an int x value of 2. From the right, our function value is 3. And so our double-sided limit, or the limit without a little plus or minus, is going to be if these are equal. If they are equal, it would be that number. If they are not equal, then it does not exist. Okay? So. And finally, we're down to our last problem, which is recall the limit as x approaches 0 of 1 over x squared. We can look at this graphically, but we need to remember what the graph of 1 over x squared looks like. And if you remember back to that hyperbola worksheet, the graph of 1 over x squared is like this. Otherwise, you can always find it in your calculator. And so, as x is approaching 0, from both sides, our graph is approaching infinity, which means there's no value to our limit, but we can say that the limit is approaching infinity. It's continuing to increase and increase and increase and increase. But we would say that L, the limit value, is not defined because infinity is not a number. And so we're going to look at these next 3 by looking at the graph of sine of x over x. So into the calculator, we're going to type in. So into the calculator, I type sine of x divided by x, and we're looking in radian mode. I know it doesn't say it here, but we're going to go ahead and do radians because that's our default. So we're going to go into mode, make sure I'm in radians, and then I'll hit graph. And so we end up with a graph that looks, ooh, what is happening? So if I look at this, this is what it looks like. Well, okay. This is what it looks like on the graph. Right? So it looks like it's symmetric over the y-axis, but let's see if we can zoom in a little bit to see what's going on a little bit clearer. So it's definitely wider than we usually think of for our sine function, right? But what's happening as x approaches 0? So again, we can't trust the graph. It looks like it's around 1, but let's go to our table. So I'm going to go to my table set, make sure I have really small increments around 0, go into the table. Now again, error at 0, so that's why we can't always trust our graph, but it is getting closer and closer and closer to 1. So our limit here is 1, and it's getting closer on both sides. So I can say with confidence that my double-sided limit or my two-sided limit is 1. Okay, what happens as x is approaching infinity? Well, I can't go out to infinity on my calculator, but what I can do is I can say, well, what happens when the values get really big? So I'm going to go into table set, and then instead of taking small increments, I want big increments. So I'm going to change this to 10. And I want to know what's happening at infinity, so let's look at what's happening around 100. And then maybe we can get an idea. So I'm going to go into the table, and I can say, wow, okay, so 0, 0, and then that has 4 zeros leading, and it's going between positive and negative. But, so it's oscillating kind of between positive and negatives, but they are continually getting smaller and smaller and smaller absolute values. So kind of like the sine function, except that it's getting closer and closer and closer to the x value, which if you think about it, I'm taking the sign values and I'm dividing them by x. As x gets bigger, I'm dividing them by a bigger and bigger and bigger and bigger number, and therefore it should be getting closer and closer and closer to 0. Even though it oscillates, even though it goes back and forth, they're getting closer and closer and closer to 0. Okay? So go ahead, look back over those notes, write your summary, and then you'll